All right, welcome. Today we're going to dive into a concept that, believe it or not, affects pretty much everything, from your morning coffee to a massive manufacturing line. That concept is variation. We're going to learn how to understand it and, more importantly, how to control it using a really powerful tool called statistical process control.
So you know that feeling, right? One day your coffee is absolutely perfect, and the next day, it's just okay. Or maybe one delivery shows up in a single day, and the next one takes a whole week. Why all the inconsistency? It's something we've all experienced, and it turns out there's a very real statistical reason behind it.
And yeah, the simple answer is just one word: variation. It's the natural wiggle and wobble in any process. Look, no two things are ever exactly the same. The goal isn't to get rid of variation completely. That's basically impossible. The real goal is to understand it, manage it, and, crucially, to know when it's waving a red flag that there's a real problem. Okay, let's make this real. Take a look at this table. It shows the number of insurance claims processed each day over a 2-week period. So Monday of week 1, we've got 42. The next day, it jumps to 55. Then on Thursday, wow, it drops down to 38. Just by staring at this, can you spot a trend? Is performance getting better, worse? It's really tough to tell just from a wall of numbers.
And that right there is our first big lesson. A raw list of numbers doesn't really tell a story. It just hides all the patterns. To make any sense of what's actually going on, we have to turn those numbers into a picture. We need to literally see it. So how do we do that? It's actually incredibly simple. First, you take your data points and you just plot them out over time. Then you connect the dots with a line. And voila! What we've just created is called a run chart. All of a sudden, that jumble of numbers has a shape, a rhythm. You can finally see the ups and the downs. Okay, so this chart is way better than the table, for sure, but it brings up a really important question. We can see the process bouncing around, but is this just the normal, everyday noise we should expect? Or is a big dip, like that one on Thursday, a real signal that something is seriously wrong? How do we tell the signal from the noise? Well, for that, we need a little help from our friend, statistics. And this is where the normal distribution comes in. You probably know it as the bell curve. This shape is absolutely fundamental. It turns out that a massive number of processes, both in nature and in business, follow this exact pattern. Most of the results clump right there around the average, and then they get less and less frequent the further you get from the middle. Now, here's where it gets really powerful. For any stable process that follows this bell curve, we can start making some solid predictions. We know that about 68% of all the outcomes will fall within a certain distance from the average, what the stats folks call one standard deviation. And if we widen that range out to 2 standard deviations from the average, well, now we're capturing about 95% of all our outcomes. So you'd expect 19 out of every 20 data points to land somewhere within this wider band. And if we go out one more step to 3 standard deviations, we capture a staggering 99.7% of pretty much everything. That means 997 out of 1,000 outcomes will be in this range. A data point outside of this is incredibly rare. That is, if the process is stable and predictable. This whole 68, 95, 99.7 thing, it's like our secret code. It gives us a statistical framework to define what's normal for any given process. It lets us draw some lines in the sand and say, hey, anything inside these lines is probably just random noise. But anything outside, well, that might be a real signal we need to pay attention to.
Okay, quick sidebar here, but this is a really critical distinction. When you hear standard deviation, think about measuring the height variation of every single person in a huge crowd. But for what we're doing, we're usually looking at smaller groups or samples. That's where standard error comes in. It's more like measuring the variation between the average height of different groups. It's just a more precise way to track the stability of the whole process. So let's recap. We have our run chart that lets us see the data, and we have the statistical rules that let us understand predictability. It's time to put them together. We're going to upgrade that simple run chart into the main event, the control chart. Let's build this thing step by step. First, we start with our basic run chart. That's our data. Second, we draw a line right down the middle for the average. That's our center of gravity. And third, this is the magic part. We use that standard error we just talked about to calculate an upper control limit and a lower control limit. Now, this is super important.
These limits aren't some arbitrary goals a manager just made up. Nope, they are calculated directly from your own data. They literally represent the voice of the process. They're telling you what the expected, natural range of variation is. And why are they set at 3 standard errors? Because it connects right back to that 99.7% rule we just learned. It all fits together. You know, the source material puts it perfectly. It says these 3 lines, the average and the 2 control limits, they become the absolute foundation for a real control system. It's what turns a simple picture into a powerful tool for monitoring and managing performance over time.
So it seems pretty straightforward, doesn't it? A point falls outside the lines, you sound the alarm, and you go figure out what happened. Simple. But in the real world, it's a little more complicated, because anytime you make a decision based on data, there's always a chance you could be wrong. And there are 2 main ways you can be wrong. You could have what's called an alpha error, which is basically a false alarm. That's when a data point falls outside the limits just due to random chance, and you end up wasting time investigating a problem that doesn't even exist. Or you could have a beta error. That's a miss. This is when the process really has changed for the worse, but the data point just happens to fall inside the limits, so you miss the signal completely. And the costs of these 2 errors are totally different. An alpha error, that false alarm, it just costs you some unnecessary effort. It's annoying, but that's it. But a beta error, a miss, that means your process is failing, and you don't even know it. The cost there isn't just effort. It could be a faulty product going out the door, or a service failing a customer. So what does this all mean? The crucial takeaway is this. Statistical process control isn't a crystal ball. It's a risk management tool. Setting those limits at 3 sigma is all about finding an economic sweet spot. It's a calculated balance between the cost of chasing down false alarms and the potentially huge cost of missing a real problem. It's about making smarter decisions when you don't have all the answers. So the next time you run into some inconsistency, maybe don't just see it as random chaos. Instead, ask yourself, what's the average here? What's the normal range of variation I should expect? And is what I'm seeing just noise, or is it a real signal that something truly needs to change? Thanks so much for joining me.